Okay, welcome everyone back for the part 2 of our session this morning, actually afternoon now. We're going to start off with Ruven Pillay from the Ministry of Culture in France.
Thank you. Is this working? Yeah. So my name's Ruven Pillay. I work at the IIIF in Paris, which is part of the French Ministry of Culture. And I'm going to give you a little talk showing an overview of how we've been using image visualization at the IIIF over the last couple of decades. So for those of you who don't know, the IIIF is a kind of the French National Research Laboratory for Art and Restoration. It's not public facing, so it's really professional facing, so maybe it's not so well known. So we're underneath the Louvre Museum in Paris, and we have these custom built facilities deep underground, under the pyramid and under the Louvre. But the centre itself has existed in various forms since 1931. Originally it was the scientific laboratory of the Louvre, and it's really a heritage science institution. So we are doing typical heritage science stuff, analyses on pigments, using various typical techniques, but also we have a kind of mission to develop new analytical techniques and things like this. So here you see we actually have a particle accelerator hidden under the Louvre, where we analyze minerals and gemstones and other types of materials, where the particle accelerator can really give us information that no other techniques can produce. So we try to use a kind of range of different analytical techniques, scientific techniques, on works of art. So obviously one of the main techniques is imaging. So scientific imaging, technical imaging of paintings, of statues, has been something that all heritage science institutions have used for a long time. So in terms of multimodal imaging, a typical painting will be imaged using a number of techniques, so typically X-rays, infrared, raking light, UV, anisotropy, color imaging. So there's a whole range of imaging that needs to be accessible and needs to be usable. So there's been a need for interoperability and visualization since the beginning, really. And going back to the late 90s, there were projects, European projects, to kind of make these image sets usable, because at the time, these image sets, we didn't have server infrastructures to manage these. These huge images, sometimes from an X-ray, they were scanned one-to-one, DPI, resulting in huge multi-gigapixel type size images. And these images were all pretty much unusable because the computers at the time were not able to even read these images into memory. So there was a need for some sort of delivery system which could transcode on the fly these images and make them accessible throughout the institution, and also to share them with other institutions. So we had this project called the Visium project, which started in '96, and the partners were the IIIF, as well as the National Gallery of London, the University of Southampton, and some other institutions. And the idea was to be able to share images in the same way that IIIF does now, share images between the National Gallery and the IIIF and also other institutions, using internet-based technologies. So this is really at the origin of where the IIP image server comes from. So, yeah, by the way, I didn't tell you at the beginning, I'm also the maintainer of the IIP image server software, and I'll tell you a little bit about the latest release at the end of this talk. In terms of APIs, this has evolved obviously with time. So IIP Image adopted this thing called the Internet Imaging Protocol, which was actually developed by an association called the International Imaging Industry Association, which involved Kodak, it involved HP, and a number of other major companies at the time. And they developed this kind of protocol, this kind of API, to access images online, so in a similar way to IIIF, but using the kind of norms of the time. And they developed their own kind of file format called FlashPix, which was designed to be able to do multi-resolution encoding and things like this. And obviously afterwards, there were things like Deep Zoom, Zoomify, which came along, which were a little bit simpler because they relied on pre-rendered tiles. So the idea behind the Internet Imaging Protocol is that you would have a server which would transcode on the fly. And well, later on, of course, IIIF has come and has kind of combined these two methods. So this image server-based approach, and also the possibility to have static file systems. So IIIF kind of combines these historical threads together. So my image has gone wrong. So those are kind of classic image techniques, but we've moved on to things like multispectral and hyperspectral imaging. So on the left here you have filter-based systems, which we started to adopt in the early 2000s. And here's a hyperspectral system, which has come off the screen, I don't know why. So here you're capturing up to hundreds of bands per pixel. So how can we visualize this kind of thing? So this is a little demo. This is live online, so you can zoom in, access the different wavelengths. So this is a multispectral image. Let's go into the infrared, and you can flick between the different views, and you can click on a point, and you get the spectral response in real time, right? So similarly, something that's become more and more used in the heritage science field is macro 2D XRF. In this kind of case, you're doing X-ray fluorescence at each point on the painting, and you're making a mapping which shows you the elemental distribution at each point. So this has become something widely used within the heritage science field. Scan times for these kind of things can take hours or even a day for one small painting, and the result is a map showing the elemental distribution of typically iron, lead, zinc, etc. So with this information, you have access to the material composition of the pigments, and this is something that's become really useful for heritage science. Managing this kind of data has been ad hoc until now. So we were looking for a way to kind of manage this in a more rational way, because this data, underlying data, is actually floating point data. It's not just 8-bit JPEGs or whatever. So how can we combine all this together? Because at each point you actually have a spectrum. So this is very similar in a way in terms of structure to hyperspectral and multispectral imaging. So here's a little example of an interactive viewer for this. So let's have a look. So you got a zoomable view here in the middle. You've got an interactive graph showing the global composition of the various elements for the painting. You can click on any particular point, any particular element, and you get the map for that particular element. And if you click on a region, for example here, you get the specific spectra for that point. And you can also do image processing on the fly, switch to linear stretch, histogram equalization, all this kind of stuff. So the idea was to make XRF mapping accessible online, and also to rationalize how we were storing and using this data. So I'll tell you exactly how in a second. And then actually all these new techniques do have something in common. So let me show you another example. This is computed X-ray tomography. So you're using an X-ray image and you're turning the object and you're making, it's like a CT scan in medicine. You're doing this on a larger scale and for things like statues. This is an example where you have an object embedded within the middle of the statue. So so you can't see it with the naked eye. And in the X-ray, if you just take one angle, it's difficult to make out where exactly it is in 3D space. So using CT scans, X-ray CT scans, you can look through the statue. So another kind of technique we've kind of adopted is to use stereo vision sometimes. Sometimes this can be useful. Here's an example. So you've got this kind of object, and we're combine different modalities plus stereo imaging. So if I go into the UV fluorescence kind of mode here, you can see areas where there's a fluorescence in some regions. So if you had 3D glasses, so just using anaglyph type glasses, cyan magenta, I have a pair in my bag, so if anyone's interested, you can try it out. You can actually see in 3D space where some of these fluorescences are coming from, and this is actually quite useful for identifying regions of retouching, or in this case, you're locating zones of Egyptian blue pigment which have left a trace, which have disappeared everywhere else, but have left a trace in some areas here. And okay, in terms of this kind of range of different techniques, I'm going to just talk about briefly RTI as well. So we've adopted, we switched to Relight as a kind of processing software, and again it has a nice nice viewing interface where this is all embedded into our collection management system. So you have access to the RTI viewer online in a unified kind of way. So where's this all going? So we've moved from what are images, so just 2D pixels on a canvas, to data cubes. So there's a third dimension of information. So even in the RTI example, you have multiple planes or coefficients for each pixel. So it's all of these new types of techniques generate these cubes. So how can we store this data in an optimal and unified way? So the problem until now is that each of these types of techniques, they have their own kind of custom formats, their own custom ways of storing data, of handling data. So we were looking at how can we unify the whole pipeline from classic technical imaging to data cubes. If we look at what exists in the field, so in terms of multispectral, hyperspectral imaging, people generally use a format called the NV format, comes from the NV software. In terms of XRF and other synchrotron-based kind of techniques, there's these formats, EDF. Pure data formats such as HDF5 are very flexible data formats that come from the big data fields. And then you have these more image-oriented formats such as JPEG 2000, TIFF, which a lot of you use. Now, if we compare these formats and we're looking at their use for data cubes, actually TIFF kind of stands out. It ticks all the boxes. JPEG 2000 has some flaws. It doesn't really support floating point. So actually, TIFF ticks all of the boxes in terms of flexibility, in terms of the ability to do multi-resolution, random access, handles metadata, compression. So the idea is that we've standardized our entire imaging stack, so even including data cubes on TIFF for both images and data cubes. So in a way we're following work that's been done in the microscopy field. There's something called the open microscopy environment where they've developed, they've adopted TIFF as a format for their microscopy slices, stacks. So TIFF is a flexible format. You can store it in tiles, planes. You have multi-image support, multiple bit depth support. You can support floating point, and it has strong metadata supports multiple forms of metadata, and it's widely used in the scientific field. And you can have this pyramid structure where it's very efficient to view very high resolution images. So as I said, our entire stack has moved to, well, it was based on TIFF, and we've now integrated all of these extra types of imaging into TIFF. We use lossless compression, or deflates compression, to optimize for space reasons. There are other compression forms which are supported by libtiff, but not necessarily compatible in Photoshop or other software. So we need these images also to be compatible with proprietary systems and stuff like this. Each of these kind of new imaging techniques still requires a specific kind of custom viewer. So we have our IIIF manifests generated on the fly by our collection management software, and we have IIP as a backend. So I mentioned I'm the maintainer of IIP image, so we just released version 1.3 just last week. And there's some nice features here which may interest you. So we've got this new low latency pass-through mode. Effectively, you eliminate the decode, re-encode cycle for browser native TIFF compression mode. So most IIIF servers will decode the image from the file and then re-encode it to the format you ask for. In some cases, this is unnecessary. If you're asking for a JPEG format and the original TIFF has JPEG compression already, and you're doing unnecessary work. There's a new fast, efficient JPEG decoder. So if you're reading just a normal JPEG, there's a new direct fast decoder for that. There's new output support for AVIF. So AVIF is this new, recent, next generation image format based on the AV1 video codec. It handles HDR images and high bit depth kind of images. There's some IIIF enhancements I'm going to tell you about in a second, and you can get more details on the web page. So first of all, this low latency mode is actually something worth looking at in more detail. So as I said, normal image servers decode and then recode, re-encode the source image depending on the output you want. So obviously, if you're applying some image processing such as resizing or rotating, then you do need to go through this whole cycle. But in most cases, in a lot of cases, this isn't necessary when you're doing pan and zoom viewing, which is one of the main use cases for IIIF. And the idea is to have both small file sizes and fast decoding speeds. So this only makes sense for JPEG and WebP. So within TIFF, you can encode using various lossless and lossy formats, compression formats. So you can encode your TIFF with JPEG tiles or with WebP tiles. And these, of course, only work for tile requests that match exactly the TIFF structure that you have within your file. So obviously this is ideal for pan and zoom use. And the interesting thing is you get close to static file performance. So you have in IIIF the notion of static export as a level 0 IIIF service. So here you're kind of trying to get close to both static file performance and yet maintain the functionality of an image server. Now, of course, this only works for TIFF, it won't work for JPEG 2000. So what kind of difference does this make? So here's an example. So I've taken an image which is reasonably big, so 15,000 by 11,000 pixels, and I've used OpenSeaDragon to just do pan, zoom, kind of typical use case for IIIF. And here in the graph, so on the left is the pure tile decoding speed, and so this first bar is showing speed without this new mode, and you can see, yeah, as you would hope, you would expect, or even hope, this kind of thing reduces the average tile decoding time quite considerably. It's about an 88% to 88% reduction in tile decoding time. Of course, tile decoding is not the whole picture, because if you look at the whole processing time, there are other things happening. So on the right, you're looking at the entire response time from initial sending of your request to receiving the result. But even here, you get a 65% reduction in processing time. So this is the average processing time on a pan and zoom of that image. So some of the requests still require a full decode recode. When you're at the edge of an image, when you need to crop the tiles, this still has to be fully decoded, encoded. So on average, you're getting, even with a mix of this low latency and full recode, decode, you're still getting a 65% reduction in the latency. So it's worth upgrading. If you're an IIP image user, it's worth upgrading to 1.3 for this. So I mentioned efficient JPEG decoding. So JPEG is not an ideal format for use with an image server. It doesn't support random access, nor tiling, but people have JPEGs and they don't necessarily want to transcode. So we can exploit the fact that the JPEG format itself uses these blocks of 8x8 DCT, 8x DCT structure, which allows you to do a kind of trick where you can downsample up to a factor of 8 just by discarding tiles. So it's obviously much slower than TIFF, but it avoids the need to transcode. So a lot of people don't want to transcode into JPEG 2000 or TIFF. So what kind of performance does this give you? So let's have a look. We're going to do the same kind of thing as we did before, with a pan and zoom kind of simulation. And we're going to do it per resolution level and relative to the decoding time for a TIFF image. So this is the full resolution on the left, and then half resolution, quarter resolution. So when we look at the first bar, this is at full resolution. So we look at the scale, it's 300 times slower than the TIFF. So it's usable, but it's slow. Fortunately, TIFF is very fast, so 300 times is still usable. And you can see it gently drops off, and then, as you would expect, it suddenly, it progressively, and then suddenly accelerates away because you're beyond the 8x8 DCT block size. So after about 1/16 of the size, it becomes a little bit too slow. So let's benchmark this. So it's 300 times slower than TIFF, but how does this new decoder compare to, say, Cantaloupe? So we mentioned Cantaloupe earlier on this morning. So using again OpenSeaDragon, I'm going to use a 4000 by 4000 pixel image because we've seen that it drops off after. If the image is too small, then you shouldn't be using JPEG anyway. So we have an identical sequence of IIIF requests we send to IIP image and to Cantaloupe, so the latest version of IIP image and the latest version of Cantaloupe. And so we get this kind of graph. So this is response time, so the lower the better. This is IIP image on the left and Cantaloupe on the right. So we have like a 10 times faster processing time with this new version of IIP image compared to Cantaloupe. So if you're thinking about adopting IIP image, I think it's probably, if you're interested in speed, it's maybe worth it. So I said there were some IIIF enhancements in this latest release. So the current image API defines a limited set of qualities. So this has been around since version 1 of IIIF. So it hasn't really evolved. So you have color, gray, bitonal. The spec allows you to add extra qualities. There's a field for extra qualities. No one seems to actually have used this until now. So I thought, well, why not add some of these new things? And it opens up a discussion whether the image API should add new features or not. Maybe it doesn't need to define new qualities. We can just, each image server can just add in this extra qualities field, new things. Anyway, so this new version introduces contrast stretching, histogram equalization, inversions or negative, and log transform. You can use these in exactly the same way as the other existing qualities. These are disabled by default. I didn't want to upset any purists, so these are disabled by default. But you can activate it quite easily just with a flag. So let's see an example. Here's a painting by Van Gogh. So what if I want to render this in a negative? I want to invert the image and have an image negative from this. You just add negative as your quality, and it works in exactly the same way as the other thing. And histogram equalization requires, the implementation is actually quite efficient. Normally histogram equalization, you need to calculate the histogram of the entire image, which can be quite slow. There's a kind of fast trick used by IPMage to make this go really, really fast. So my time is up. Just to tell you, this new version just came out last week, so you can download it. There are binary packages for Windows, Solaris, macOS, package managers. Alpine has already upgraded to 1.3, and hopefully Debian and the others will do so soon. As Docker, people who prefer to use Docker, there's an official kind of Docker image which is already on 1.3, which has these features activated by default. Just last thing on future directions for IPMage. So in terms of these qualities, the things like PCA, de-stretch, which is used in the archaeology field and things like this. These could make interesting future qualities. We're going to look to support HDR output, so like 10-bit and other high dynamic range output forms, and look at using hardware acceleration such as GPU acceleration using CUDA, things like that, for the image processing function. So for more information, go to the website or post an issue on GitHub. Thank you.
Thank you. Next up, we have John Cameron from Indiana University Libraries.
Hello, everyone. I'm John Cameron from Indiana University Libraries, and today I'm going to talk about content search and how we've implemented it in the software that we developed, Avalon Media System. Spilled some water, Glenn, I'm sorry. Avalon Media System is an open source repository platform. It's off-the-shelf software for managing and providing access to collections of digital audio and video. So it's meant to be repository software that you run for your institution. Some of the big marquee features are very detailed access control settings and a simplified transcoding pipeline with file management. So it's in use at quite a few institutions, including IU, where we use it very heavily. So IIIF is in many different places in Avalon. We have implemented several of the APIs. Foremost is, of course, the presentation 3.0. We have manifests that are available for all media objects. We also have an implementation of auth 1.0, which is applied just to restricted access objects and works with our authentication for streaming resources. And then we just implemented Content Search 2.0, which is used for searching specifically in Avalon for within transcript documents. So we have other software in Avalon that uses IIIF. So the biggest one is RAMP, which is our media component library written in React. It reads manifests and renders different things out to the page depending on the components that you configured. We also have a structural metadata editor, which is defining tracks or sections of ranges. that uses IIIF under the hood, and then Timeliner, which is a piece of software that is separate but built into Avalon that creates bubble diagrams to annotate audio and video resources visually. So going back to RAMP. So RAMP is our library of interactive audio components. So you can see it listed out here. We have a Video.js based media player, descriptive metadata display, the transcript viewer, and a bunch of other things that are all separate components that can be arranged or added or removed as needed. So again, the default in Avalon now is to produce a presentation 3 manifest, and when an item page is loaded, RAMP will initialize, read the manifest, and then populate all the pieces. So there are other players. Our goal for RAMP is really to just have a very lightweight, accessible player, and also something that satisfies a very broad set of use cases. Let's see. So content search in Avalon. In Avalon 7.8, we implemented content search 2. So we have a search service that's available in our object manifests that is set up with a search service specifically for media files themselves. So we have the media object, and then which can contain any number of media files. And then any media files can have any number of transcript documents. And with one search service, we query all of those. So we use Solar behind the scenes. So Avalon is a Sanvera product, and we use the traditional Fedora with Solar for fast index. So everything we basically put into Solar and wrapped with Solar API calls, and that's how we build the content search responses. Yeah, so big reason we wanted to do this was because of work on the transcript component within RAMP, which we added a search within functionality to. So RAMP will call out to the content search, get the response, and then process it and render that. So the transcript component itself is, just kind of a little thing. It renders a few different file types. It has, navigation that you can use if your information is timestamped. Let's shout out Third Wave, which is the company that decided to adopt RAMP and initially wrote most of the work for the search within feature. And in RAMP, we set it up specifically. So their use case had nothing to do with content search. So the way this is written, you can either use a local transcript document. So JavaScript will just index it and be able to populate any search queries, or you can hook it up to a content search service like we do in Avalon. So we did want to scope it pretty tightly. Again, this was only just going to be for transcript documents only in Avalon. So you can see an example of our URI where it's basically, we have the media file, we call them master files in Avalon, an identifier, and then the search query. So that hangs all off on that master files route. And again, when you do a search, like this example here, you'll get back hits from every transcript document associated with the media file. And then it's up to the viewer to render that out appropriately. And each match result will be just a unique item when the annotation page comes back for the content search service. Yeah, so this is kind of what it looks like in an example. So we have RAMP's transcript component there. It has things, so it's got the search inputs, a pager, a drop-down, so you can select which of the transcripts you want to view and render down there. And then, highlighting and different ways of rearranging things. When you search, we also added it so that you get visual time points for each match in the media reel itself. So our primary use case was transcript text. So we started adding the ability for Avalon to store transcripts and continue to work on that. But we do support primarily VTT, but also Word documents, and then SRT and plain text. So the first step was really how do we get this stuff into our index. Everything was just files on disk. And searching that way wasn't going to work, so our idea was we'll just add the contents of the transcripts to the Solar index and use built-in Solar queries to basically get that information out and use it to populate the API response. So every document that goes in, the new standard is we get everything normalized. So removing new lines or any other things that we want to do for encoding, we chunk it up where it becomes a series of things or a series of sort of paragraphs within the Solar index, and then we can query that based on any sort of media file that's in there. We do the chunking by timing information if it's available. So for VTT and SRT, we would expect that. For Word documents and plain text files, we just ignore it if it's present. In the future, we'd like to add that back in. But right now, we're really expecting that if you want to use time text functionality, you're going to have an SRT or a VTT file that you upload. So when we went to implement content search, there are a lot of examples. A lot of people are using it. Not a lot of people using it for our specific use case. So most people are using spatial dimensions rather than temporal dimensions. But basically, we took a look at a lot of examples that people were using for the responses they had in their content search service and just kind of patterned it based on everything that we found. So again, we're populating this or implementing it with Solar. So Solar is kind of like our source of information that we use basically in many different ways. So now that we have the search text or the text of the transcript in the index, we can query it pretty easily. So we query Solar and we get a JSON response back. And then we transform that, therefore, then to the content search response. So in content search, you expect it to return as an annotation page, which it does. The search service itself is defined in manifests at the canvas level. So it will only appear at the canvas level and just for these media files, and that's sort of where we left it. So if you're like me and you like looking at key value pairs, here's an example of an item from one of our API response calls where I did a search for leaves. So there are a few interesting things here. One, our motivation will always be supplementing the guidance is to have it match the motivation that you originally had, and all of our resources are supplementing motivations. Let's see. So again, I mentioned the temporal dimension. So we have timestamps or time codes at the end here that are used for the target that are represented in NTP time right now. So we'll probably want to move that into seconds, but they'll show up as range if possible, separated by comma, hour, minute, second, milliseconds. And then it's kind of funky. You see, like here in the textual body, the value has these M tags with this Unicode encoding wrapped in there. So this is how our search service comes back, which seems a little funky, but that's the way Solar delivers it to us, and it worked really well within the implementation that we had within RANT for putting it into the transcript component and then having it render out to the user. So that's currently the way it works. There's an emphasis tag that's written in that highlights the search query or the search text within the greater chunk or the queue that happens. So I think our big concern at the beginning was performance. So if we are, going out to a service for a search and then repopulating back in, that's necessarily going to be a lot more latent than just querying a local document in memory. So we did a bunch of testing and ultimately got to a place where it was acceptable. It's not as fast as a local index, but it worked well enough for our use case to make it seem reasonable, especially when you're actually using it. So yeah, right now I was testing, it's usually less than 200 milliseconds for the server response itself. Everything around that can vary, but it's pretty acceptable, especially when you start typing in the search box and search results start coming automatically. Let's see. So there are a bunch of limitations. So yeah, there's a bunch of stuff that we could be doing with content search, but of course for this initial implementation, it was pretty much this use case for only transcripts and only on media files. So there are a lot of things in the API that we didn't add in. So there's no paging support, autocomplete support. We don't support all of the query parameters in the spec, just the mandatory one. And the big one is no match highlighting or context. So if you look at the spec, you'll see you can do different things, especially with selectors, where it's basically doing sort of in a weird way what Solar is returning with. Instead of the emphasis tags, the API response will say, here's the actual text and here's the text beyond it. So we're kind of simplifying things to, make it work, but there are a lot of ways that we could be massaging this a little better, especially in the future for wider support in the ramp. So for this first implementation, we basically said, we'll implement the spec, we'll get it working in ramp, and then we can sort of revise and look to the future. Indexing text from documents other than transcripts. We have transcripts and captions are, of course, most of what we're dealing with, but there are other textual documents associated with media files that we would want to support. Things like audio description as well, which we haven't really started working on, but is an example of a supplemental file that we would want to index and be able to search. And then the search routes themselves. So again, right now, the manifests that we generate are limited to those media items. And expanding it out will allow us to expand content search out, so it would be great to do it at the item level or the collection level, get results, I think that's about it. So I think we have some things to do. I would like to keep working on this, but for right now, it's worked really well as an implementation, just functionality wise within RAMP and then within Avalon. Thank you.
Thanks, John. We do have time for questions.